Good morning. So the clock strikes 9 and I'll begin. And I will begin by fixing an error that I made. Not last lecture, but the previous lecture, and I just forgot to mention this last time. And the error was in the formula for the second derivative of a composition. And I had it right the first time I wrote it down, and then for some reason I convinced myself that it was wrong. And I changed it. Let me fix it. And also, because I um, decided my first correct thing I wrote down was wrong, I also screwed up how to calculate this thing, but it's easy. Um, the first derivative of a composition, of course, is given by this, which is the usual formula for the chain rule. And then when you differentiate this thing again, the way to do it is to use the partial derivative rule, which says that, so I'm going to differentiate this thing as a function of these variables. So you get, so first we're going to differentiate it with respect to x, okay? And so you're going to get d2 psi by phi at phi of x, okay? First let me put the right thing in here. So u1, u2, okay? So I'm going to get this. So I'm going to differentiate this thing, okay? And I'm differentiating now with respect to x, which means I'm differentiating with respect to the first component here, okay? And so when you do that, we're going to get this thing is fixed because we're differentiating with respect to the first component. So you get d vx u1, and then by the normal chain rule, d vx u2, right? So that's differentiating with respect to this component, and then you differentiate with respect to this component. Okay, leaving x fixed, so that means we're differentiating in this slot. But the derivative as a function of u here depends on x, so you have to also use the chain rule here. And so you get d psi at phi of x, d2 phi of x, u1, u2. Like that. Okay, so that's the correct formula. And like I said, I had that right the first time I wrote it, and then I convinced myself that I was wrong, which is usually a successful strategy, but it turned out not to be right this time. Okay. All right, good. So I just wanted to fix that up. So we're talking about vector bundles. So let me sort of summarize where we are with vector bundles. So we had defined the notion of a vector bundle, which has a total space E, a base space M. And remember that the base space is a set of points in E, which when you represent those chart, they correspond to the point 0. The vector part is 0 in the vector bundle chart. Okay, so that's the base space, and then there's the projection from E to the base space. Okay, and then we had the notion of a fiber. So if you take a point X in M, then the set of all points which map to X is called the fiber. I don't think I introduced this notation, but common notation for the fiber is E sub X. Okay, and then at the end, we defined the notion of a vector bundle mapping. So we have two vector bundles. And then a vector bundle mapping is most easily represented by a diagram. So I have, first of all, a mapping, phi, which maps the total space of E to the total space of F. And this mapping induces on the base spaces a mapping which I call phi naught. Okay. And the idea is that this mapping phi takes a fiber over a point in M and maps it to a fiber over the image of that point under the mapping phi naught. Okay, so I have this diagram means that I have a mapping like this, phi sub x, which maps the fiber at x to the fiber at phi of x, and so that there exists a mapping like this. That follows from the diagram, okay? And it's a vector bundle mapping when this thing is linear, okay? Okay, good. So that's where we were. And so today, what we're going to do is talk about various constructions of new vector bundles from existing vector bundles, okay? And there's a variety of ways of doing this. And I will not be going through all the details for all of this because it gets kind of dull and repetitive and sometimes excessively detailed. So I'll give the constructions and outline, kind of how it works, and then uh, that'll finish our discussion of vector bundles, and we'll move on to talking about what are known as affine bundles. Okay, so new vector bundles from old. So let's first talk about subbundles. Okay, so we're going to let phi be a CR vector bundle. And R is the usual thing. So a subbundle. Subset F of E is a subbundle if, okay. So a subbundle is rather like a submanifold, and in fact it is a submanifold of a particular form. Okay, so the way you define it is like you define submanifolds by the existence of a special kind of chart. So if for each x in M, there exists a vector bundle chart about so sorry, let me give the notation for this thing. So it's going to be the vector bundle charts we had written as V psi. Okay, so V psi is a subset of E. And vector bundle charts, the codomains look like products. Okay, and so remember the idea was that these are the fibers and the base, the points in the base space get mapped to here. Okay. Okay, and so this is a vector bundle chart about X. Okay, so this makes sense because X is a point in E also, as well as being a point in M, because M is a submanifold of E. Okay, and a sequentially closed subspace W psi, and W psi is a sequentially closed subspace of the fiber part, such that Okay, and so the idea is rather like what you do with submanifolds. So you're interested in how these things um, look like, um, how points in F look like when you take their image under the vector bundle chart psi. Okay, and the condition is um, rather like a submanifold type condition. So it's psi of, okay, so you take the points in F, which lie in your chart domain V psi, okay? So the image of this is going to look like the psi of V psi intersect, okay? Um, So they're going to be points which in this component live in W psi. Okay, so it's going to be uh, V psi naught cross W psi. All right. Okay. Okay. Let me just make sure this is enough. Okay. Um, yeah. So and such that. Okay. Um, psi of V psi intersect. Okay, so we want the points which are in the the V naught part. We want those to be the same as those which come from this. Okay, so let me code that like follows. So W, V psi, V psi 0 cross 0, okay, is equal to psi of V psi intersect F intersect V psi 0 cross 0. Okay. All right, so this part, make sure that the fiber part of F, okay, is restricted to this subspace W psi, and then this condition here says that the base points are not restricted. Okay, so the points in the base are going to be represented by points which map to points like this in the chart codomain. Okay. Hopefully that makes sense. Okay, so that's what a subbundle is, right? Just insert a bunch of pages here. Okay, all right. So note a subbundle has two immediate properties from this definition. Is a submanifold of E. Okay. All right, and what this tells us is so this is a particularly awkward way of saying something very simple. So let me maybe write this in its more simple fashion. Okay, so let me maybe postpone. Um, oops. Um, sorry, postpone this because both statements that I make are going to be obvious when I sort of encode the definition in a slightly better way. If psi of V psi is equal to, let's say I have some, so it's going to be a subset of V0 psi cross V1 psi. And the point is that the image of the chart domain is going to be a local vector bundle. And so this is going to look like, let's say, O cross V psi 1. Okay. And then this condition here, okay, combined with this condition here means that psi of V psi is equal to O cross W psi. Okay, so that is a simpler way of encoding the two conditions that I gave for a subbundle. Okay, so if you use these two conditions, so thus we see that a subbundle is two things immediately. It's itself a vector bundle. And a submanifold of E. Okay. Um, and both of these things follow immediately from the fact that the image of a subbundle under a vector bundle chart looks like this. Right? You know, and you have to still do some things here, right? So you still have to verify to say that something is a vector bundle. You have to make it clear what the vector bundle structure is. Okay, and so the vector bundle structure for oh, sorry, I made a mistake here. That first I meant that. Okay, and so the vector bundle structure for F, okay, should be such that this thing is going to be the image of a local vector of a vector bundle chart for F. Okay, and then you have to verify the overlap condition, right? So you always have to verify overlap conditions. If you're going to say what a vector bundle is, it's not just enough to define charts. You really do have to verify overlap conditions because that's what verifies the vector bundle structure. And the reason you need to do that is sometimes vector bundles can be globally quite complicated. So we saw this example last time of two vector bundles with the same base space, right? So they both had a base space of the circle. They both had fibers that were R, okay, but they were not the same vector bundle. One was a cylinder, and the other one was what I would call a twisted cylinder, like a Mobius strip, but a vector bundle version of a Mobius strip. So it's really not just enough to verify that the thing locally looks like a local vector bundle. You have to verify the overlap conditions. Okay, so I'm saying thus we see, but there's a tiny bit of work to be done here to show that when you take a vector bundle atlas for E consisting of vector bundle charts, then these things form a vector bundle atlas for F. Okay, so you have to do those things, but I'm not going to. All right, and similarly to show that it's a submanifold, well, that's relatively straightforward. Okay, all you need to do is use this observation plus the fact that this thing is a sequentially closed subspace of that. Right. Okay, good. So that's what a subbundle is. So a subbundle basically makes the fibers smaller. Okay. All right. um, so sometimes, but not always, there's an important type of subbundle, and it's what's called split. So a subbundle F of a vector bundle E. Let me leave off regularities here. Okay, so everything's CR for suitable R. Okay, is split if, okay, um, if for any subbundle chart, okay, so subbundle chart is going to be a vector bundle chart, V psi, V0 psi, V1 psi. And then we have this sequentially closed subspace, W psi of V1 psi. Okay, so this is going to be my notion of a subbundle chart, just like I had a submanifold chart. Submanifold chart, I took the manifold chart and then tacked on the subspace that corresponds to the submanifold. I do the same thing here. Okay, for any subbundle chart, W psi is, and I'll write some words and then I'll tell you what they mean. It's topologically complemented in, so it sits inside V psi 1, okay, all right, i.e. There is a subspace. Let me call it maybe W prime psi. Sorry, V psi 1. Such that the psi 1 is isomorphic to, and I need to carefully define the words that I'm using here. So W psi cross W psi prime. Okay. All right, so there's this little line here has a ton of stuff bundled into it. Okay, so first of all, this is a locally convex space, so it has a locally convex topology. Okay, each of these are subspaces. All right, and so each of these has the product. Sorry, the induced topology. Okay, so if you have a subset of a topological space, normally without, unless you say otherwise, it'll have the induced topology. Okay, and so therefore the product. All right, so these therefore, so each of these are locally convex spaces. Okay, the product has the product topology. Okay, so that's the normal topology that you take for a product. Again, unless you say otherwise. Okay. All right. And so then this is saying that we have these two subspaces, W psi and W psi prime, and psi prime is a complement, so it's an algebraic complement. So this means that I can write any point in V psi 1 as a uniquely as a sum of a point of a vector in here and a vector in here. So that's the algebraic part of this isomorphism, but it's the topological part of the isomorphism that's most important, because it may not be the case, although these things have the topology that's induced from V1, okay? It doesn't mean that the product topology here will be isomorphic to the original topology here, even though algebraically these things are isomorphic. Okay, so this isomorphism here is okay. And so I'm spending a little bit of time talking about this, and there's a reason for it. Unfortunately, we're not going to have time in this course to really dig into it, but this is a good time to mention the issues here. So let me give you maybe an example of something which isn't complemented, just to kind of show you that there's content here. Okay, so the yellow thing should incline you to think that this is something I'm talking about, but isn't necessarily part of the course. Okay, so let's let so let's take sequence spaces. Okay, so we're going to take let's just talk about sequences of real numbers. So this is the set of mappings, let's say phi, from the set of positive integers into R. Okay, and this is, of course, just the space of sequences. Okay, so I'm going to take two subspaces of this thing. Let's let L infinity be the bounded sequences. Okay. And let's take C0 to be sequences which converge to 0. Okay. Those are both collections of sequences, and on each, let's use the infinity norm on L infinity. Okay, and the infinity norm is of a sequence. So a sequence is a mapping like so. All right, is simply soup. Okay. All right. So then C0 certainly is a subset, a subspace of L infinity. Okay. And it's closed, in fact. Okay. But it is not topologically complemented. So topologically complemented, or the absence of the property of being topologically complemented, doesn't require exotic spaces. It certainly requires infinite dimensional spaces. Every subspace in a finite dimensional topological vector space is topologically complemented. So the absence of that property is certainly an infinite dimensional property, but it just happens even for nice norm spaces, right? So these are just classical sequence spaces. Okay, so so notice that every subspace of a vector space is algebraically complemented, right? So if you just have an arbitrary vector space and an arbitrary subspace, there will always be an algebraic complement, all right? But as soon as you start introducing topologies, things get more complicated, right? Okay, so why do I um, talk about this? So okay, so so I'm going to keep writing in yellow to indicate that this isn't something we're going to talk in detail about. All right, um, split subspaces arise in the implicit function theorem for Banach spaces. Okay, so remember, Banach spaces are complete normed vector spaces. And so, what does that mean? Okay, okay. So I'm going to just very quickly and sketchily kind of tell you some version of the implicit function theorem. Okay. Right, so implicit function theorem has to do with solving equations. And so again, I'm going to be giving you just a very narrow version of this. So it's used to assert the existence, locally at least, of regular. And so regular here means of some differentiability property, and the differentiability property will be sort of inherited from the mappings that are involved. Regular solutions to equations. Okay, so let's let um, um, U, so I'm talking about normed spaces here, PU and V, PV, be normed spaces. Okay, and let phi be a mapping, let's say from an open subset O into V. Okay, so given, let's say a vector Y in image of phi, does the equation okay, so you want to find all x's so that phi of x is equal to y, have a, and so let's say that phi, sorry, let me put some regularity in here. Okay, so okay, so does the set of solutions of this equation have is the set of all solutions smooth in some way? Okay, all right. So if Um, and so now this is where we're going to use um, calculus and split subspaces. Okay, so if a d phi, okay, so the derivative, okay, so the derivative of phi um, um, at x, okay, so this is going to be a mapping from a linear mapping, a continuous linear mapping from u to v, okay, is surjective for each x in preimage of y. Okay. And if the kernel of d phi is topologically complemented in U, okay, so the kernel will be some subspace of U, and if it's topologically complemented, then the set of solutions x in O such that phi of x equals y is a CR submanifold of O. Okay, so like I said, there's other versions. This is a very simple version of the implicit function theorem. It's actually a consequence of what you would really take to be the implicit function theorem. Okay, but the point I wanted to make here is that this requires this condition. Okay. Um, all right. So that's why the notion of a split subbundle is important, is because this notion of split arises in the implicit function theorem, which is valid for normed spaces. So, okay. All right, so there is no general version of an implicit function theorem. For locally convex spaces. Okay. All right. And so for this reason, so the notion of split, therefore, is therefore not generally important beyond except for norm spaces. And I could have just said this notion of split is only important for norm spaces, but why would that possibly be? But the reason is the implicit function theorem. Okay, so split shows up in the implicit function theorem, but since the implicit function theorem just fails catastrophically for locally convex spaces, there's no point having this. There's no benefit to assuming split in general. So for manifolds modeled. Yeses. Okay, so that's my sort of aside. Okay. So that's an important topic that I just kind of quickly touched on. Okay, implicit function theorems, and the absence of these for general locally convex spaces. So, but it's one that's kind of deep and one that we're not going to be able to get into in any meaningful way in a course like this. Okay, good. All right. That's subbundle. So now back to white. All right, so what other kinds of constructions can you do with vector bundles? So we have subbundles, which are like submanifolds in some sense. You can also talk about products. And I'm not going to belabor this. So we have two vector bundles, E and F. Okay. And you can talk about the product. Okay, and this thing is a vector bundle over M cross N, and the easiest way is to draw a diagram. All right, so we have E cross F. Okay. Okay, and so E cross F maps to M cross N. Right. Um, and so if you have a point, so this is just the normal set theoretic Cartesian product, okay, and therefore it's a manifold, as we talked about last time. Okay, so it has a projection onto F and a projection onto E. And this has a projection onto M and a projection onto N. Okay, and so that kind of encapsulates what's going on with the product. Okay, and so the fiber over X and Y in M cross N is isomorphic. And so as a locally convex space to oh, so sorry. I need some a symbol here. So let me insert a symbol. So the fiber, whoops, wrong place to insert. Yeah. All right. Okay, so the fiber is going to be E cross F over X, Y. Okay, is isomorphic to the product of the fibers. E X cross F, Y. Okay. Okay. And so you again, as soon as you tell me you've invented a new vector bundle, I'm going to have to ask you to verify the vector bundle structure. So you have to do that. So, you need to verify that this thing, all right, this product of manifolds, um, inherits from each of these vector bundles a vector bundle structure. It's just notation to do that. So I'm not going to do that. Okay. The product isn't actually a super useful construction. You don't, in other words, you very seldom actually deal with the product of vector bundles like this. But there are constructions related to the product of vector bundles, which are important. So let's talk about those and see how they sort of show up from products. Okay. All right. Direct sums of vector bundles. Okay, so. Okay, so again, let's let E and F be vector bundles. And now I'm going to consider vector bundles over the same base space. Okay. So this is a very common situation when you're talking about building new vector bundles, is that you have vector bundles over the same base space, and you do stuff with essentially just with the fibers is what this means, because and when you have the product here, you're doing things with the base space as well. But here the base spaces are the same, and so we're going to be considering construction here which only works with the fibers. Okay. Okay. So one can construct, and I won't go through the details of how to do this, but I'll just indicate quickly how you do it. The outline of the construction. Okay, so one can construct um, a vector bundle over M, um, whose fibers. So sorry, again, I need to insert the notation here. And the vector bundle will be E plus F. Okay, whose fibers are, so E plus F over X. The fibers are going to be isomorphic to, and again, when I write this symbol, okay, I mean the same thing as I did here. I mean an isomorphism of locally convex spaces. So EX. We haven't really talked about direct sums of locally convex spaces. We have, however, talked about products extensively. Okay, and for finite, when you have finitely many things that you're combining, the direct sum and the direct product are the same topologically. Okay, the differences between sums and products arise when you talk about sums and products of more than finitely many things, and that's not something we talked about, and it's not something we're going to talk about. Okay, so to do this, let's just indicate how to build vector bundle charts. Okay. And then once you build vector bundle charts, you have to verify overlap conditions. Okay, and that's the thing I won't do. Because as we've seen, verifying overlap conditions is tedious. But you have to do it. But I'm not going to do it. But you still have to. Okay, so you build vector bundle charts, um, obviously by combining vector bundle charts for E and F. So um, let's say V psi V0 psi, oops, V1 psi, and let me call it kappa. Um, okay, B vector bundle charts. For E and F about X in M. Okay. All right, so there's a simplification that you want to make right away. So notice, because M is a submanifold of both E and F, okay, which we verified last time. And moreover, we verified more than just that E and F is a submanifold. We actually verified that submanifold charts are defined in the obvious way by the vector bundle chart. So remember that points in M in the chart are the points which map to 0 here. Okay, and so therefore the chart V psi induces a chart for M just by considering the mapping from M into here, because at points in M, this component is automatically 0. So um, we have induced charts. Let's say U psi, and let me call it, just because I'm going to simplify this here in a moment, phi psi, and then V0 psi, and U kappa, phi kappa, V0 kappa charts for M. Okay, so phi psi of X is going to be psi of the 0 vector in the fiber over X. That's going to be a point of the form phi. Let me write it as X prime is 0. Okay. All right. So like I said, points in M map to 0 here. Okay, so the points will look like that. And so my chart is the mapping which sends a point X, which is in M. So M corresponds to a 0 vector in E, and it maps it to a point here, with the main thing being 0 there. All right. So I'm just indicating to you how you define these charts. Okay, so with the simplification that I'm going to make is because M is a submanifold, I know that the charts for M about X are compatible. And so I'm going to make the simplification that they're the same. So we're going to simplify. So these charts are the same. And if they're not, then I just use the overlap map to make them into things which are diffeomorphic to each other, and use the diffeomorphism to make them the same. Okay, so if they're not the same, then I have to do some adjustments. So, but after adjustment, I can assume they're the same. So simplify so that these charts for M agree. Okay, so in particular, this gives that V zero psi and V zero kappa are the same, and I'll just call that V zero. Okay. All right. So then the chart for this new vector bundle. Okay. So first I should tell you, the first thing that you need for a vector bundle is a set, right? So I should at least start by telling you what this set E plus F is, okay? And so this is going to be what's called the disjoint union. Oops, sorry. Of the fibers, the direct sums of the fibers, okay? All right. So if you haven't seen the notion of a disjoint union, there's a little project for you. Okay. In your mind's eye, these things are kind of automatically disjoint, because as soon as you take 2 points X, which are not the same, then these fibers are not going to be the same. And so the union's kind of automatically disjoint. But just to be precise about it, we define this to be what's known as the disjoint union. But in your mind's eye, feel free to just think of that as being the union. Okay. Okay. So it's going to be the chart is going to have a domain, and the domain is going to be V psi plus V kappa. So this is a notation now that I'm defining. Whoops. I need to tell you what that means, and I will. Okay, and similarly, I need to tell you what this means, and I will. Okay, this one, I don't need to tell you what it means because everything's defined. Okay. So that's my chart. Okay, so remember my original things had a V. Oops, did I get that? I forget now which order I put these in, whether it's V psi 0 or V 0 psi. I think it's V psi 0. I've done both here just to cover myself. But I've assumed that the V0 parts are the same by making the charts for M the same. And so that's just the M part. And then these are the fiber parts, right? So the fiber for E and the fiber for F. And you could put direct sum there if you want. Okay, where? Okay, so what is the first two parts? The domain of the chart and the chart map. Okay, so I need to tell you that. Okay, so where V psi plus V kappa is the disjoint union of the x's in U. Okay. Okay. So U is equal to oh, sorry. There's a piece of notation that okay. I should have introduced up here. Apologies. And I'm going to write these charts here as U, V, phi 0. Okay, so these are the chart, that's the chart for M induced by the charts for E and F. Okay, so that's what U is. um, okay, so the chart domain is just going to be the collection of all the fibers over points in um, um, uh, the points in M, which are in my chart domains. Okay, psi, direct sum kappa. Okay, so it's going to take a point in here. Okay, and a point in here is going to look like, let's say, EX, um, FX. Okay, and the point is the x's are the same. All right, that's what makes this different from the product of vector bundles that we talked about before. Okay, so this is going to be phi of x, and then psi of EX kappa of FX. All right, so that's how I build my vector bundle charts. Okay. And you see some similarities here with the product, and there's a specific similarity that we're going to talk about because the fibers are the products of the fibers, or again, sums or products, it's all the same. And I'm using sum here to distinguish it from the product that I talked about before. Okay. All right, so that's how you build the vector bundle charts. So then, now you have to go through the tedium of verifying the overlap conditions. So you have to choose another chart for E and another chart for F, and then build the direct chart to the different chart for the direct sums, and then write down the overlap condition, and that's a big mess. Okay, but you have to do it. Okay. So definition, this thing we just constructed is what's called the Whitney sum. Okay, named after the famous geometer Hassler Whitney from the 30s, mid 40s, 30s and 40s, and well, 50s too. And of all the things that Whitney did, this is one of the least exciting, but it still bears his name. All right. So there's a construction of vector bundles. You take the sums of the fibers. Okay. All right. Now there's another construction which is harder to understand, and I'm not going to even define the vector bundle charts for this thing because it's complicated. So if you want to take a look at that, you can read the notes. And but it's an important construction. Unfortunately, it's a difficult one to understand. Okay, and it's called the pullback construction. Okay, so what's the setup? So let M and N be manifolds. And let we have a vector bundle, E over N here. Okay. All right. So if we have a mapping phi from a CR mapping from M to N, Okay. Then what you can do is you can do this construction that's called um, pulling back one vector bundle to another. Okay, so let's give the definition. Um, let's just define a thing which at least notationally makes sense. And I'm going to call this phi star E. Okay. This is going to be the set of points x E in M cross E, so that phi of x is equal to pi of E. Okay. All right, so that makes sense, at least as a set. You can consider this thing. All right. Whether this has any meaning or not is another story. Okay. And denote um, phi r pi. Okay. And this is going to be mapped now from phi star E to M. And it's going to take a point X and E. Okay, so if X and E are in phi star E, then they must satisfy that relationship. Okay, so when I write these points, I'm bearing in mind that they need to satisfy this relationship to be in here. Okay. Oh, and yeah. So this is just X. Okay, just the projection onto the first factor. Okay, so then, and so again, I'm not. I might chat a few words about it, but I'm not going to be. I'm not going to do anything more than that. Um, phi star pi from phi star E to M, okay, is a vector bundle. Okay, and it's called the pullback of E to M by phi. All right, and one way to understand how everything kind of fits together. So if we define a mapping, which I'll call phi hat from phi star E to E, okay, and this is going to take a point X, E, and simply map it to E. Okay. Then the pullback bundle makes the diagram E, phi star E. Okay, so I have two mappings now going from phi star E. One is this and one is this. Okay, and then this maps to also, and this is the vector bundle projection. Sorry, pi. And then here I have phi going from M to N like this. Okay. All right. So you can verify just by the definition of all the symbols involved. Okay, the definition of this, the definition of this, the definition of this, that this diagram commutes. Okay, so if you go like this, it's the same thing as going like that. Okay. But what's also true, and definitely you can't see that easily because I haven't told you what the vector bundle structure of the pullback bundle is, but I will just tell you that this diagram becomes a vector bundle mapping. So it makes this diagram into a CRF vector bundle. Okay, so that's what the pullback bundle does. So, so the notion of pulling back is an important one, because you pull back all kinds of things, and this is in fact, one of the most the least easy to understand notions of pullback, which happens to be the first notion of pullback that we talk about. But the idea is you have a mapping between manifolds, and you take objects here and you pull them back by the mapping to objects here. Okay, and here the object is a vector bundle. Okay, so you're pulling back the vector bundle E um, uh, to a vector bundle over M. All right. And the way that you build this, to verify that this thing is a vector bundle, you have to do the thing that you do to verify that something is a vector bundle. You have to construct a vector bundle atlas. And how are you going to do it? Well, you're going to do it by um, taking an atlas for M, okay, a vector bundle atlas for E, right? And from and then, so you need from a chart for M and a vector bundle chart for E, you have to fabricate a chart for this thing, okay? And that's where um, this condition is going to come in, okay? Because it connects points in M to points in N. All right, so that allows you to kind of tie together the vector bundle chart here and the chart here. Okay, and that's maybe kind of all I'll say about it, because even just to define the vector bundle charts is a bit tedious. And then you have to verify the overlap condition, which, oh my God, is really tedious. All right. So I won't do that, but this is an important construction. Okay. And me going through the flurry of symbols required to prove that this is a vector bundle is not going to help you understand it. But some examples of pullback bundles might help you understand it. So let's give some interesting examples of pullback bundles. Okay. Oh, actually, I'm going to give more or less essentially uh, um, two examples of pullback bundles, which are kind of the same. In other words, in the sense that the pullback bundles that I construct are going to be just multiple versions of the same thing. Okay, but it gives you maybe some insight. Okay, so examples. So, these aren't examples of pullback bundles in the sense that the derivative of sine x is cosine x is an example of a derivative. These are kind of abstract examples. Sometimes can't decide whether I want to hyphenate pullback or not. So I hope the idea is this might give you some um, intuition about how pullback bundles work. Okay, so all right, so we have the setup of that we had for direct sums. And in fact, we're going to build three different pullback bundles, which are all the same thing as the direct sum. Okay, so let little delta m be the mapping from m to m cross m. This is going to be the diagonal mapping, like that, which is a useful and very elementary thing. Okay. All right. So as I say, there's a variety of pullback bundle constructions that you can do here, and I'll sort of draw them all. In the sense that I'll draw the diagrams that define the pullback bundle. Okay, so we have three pullback bundles. Okay, so to denote the pullback bundle, I'm going to draw this diagram. Okay. All right, so the first one is, so I'm going to, uh, um, so I have M, okay, and then I have, let's say F, and I have pi F, okay, and then here I have E, okay, I have pi E, all right, and here I'm going to just sort of take the same construction and flip horizontal and vertical. So I have E, pi E, M, uh, okay. Now, from this diagram, right? So I've drawn this component of the diagram, and that's the data that defines the pullback bundle, right? The pullback bundle consists of this and this, right? So I've drawn that for these two things, and then on the other one is I have M cross M, then I have E cross F, right? So this is the product now. Okay, so the mapping here is pi E cross pi F. And then I have this mapping that I just defined, delta M, M. Okay, all right, so there's three things that I can just automatically build the pullback bundles. Okay. Um, Up here goes delta M hat. Up here goes pi F hat. Up here goes yep, pi E hat. Okay, and then here I have pi F. Let's see, no, pi E star F. Okay, and then pi E star pi F. Okay, and then here I have pi F star E. Okay, and then pi F star E. All right. And then here I have delta M star E cross F, delta E star pi E cross pi F. Okay, now that's, and so obviously those three things are all isomorphic as vector bundles. Okay, and if you believe that, right, but let's maybe try to convince ourselves that they might be. Okay, so what does this thing consist of? Let's just choose one of the three. Well, these two work the same. So once you've done one, then the other one's the same. So what does this consist of? So this consists of points in E cross F, all right, where pi f of the point here is the same as pi e of the point here. So these are just points in the vector bundles f and e sitting over the same point in M. Okay, so immediately the points in here are going to be elements of E cross F, okay, which lie over the same point in the base. Well, that sort of sounds good, because that means that points in here are going to all be elements of EX cross Fx, sorry, Ex cross Fx, okay? So that's looking direct summy, okay? All right, so let me say the fact. So these three vector bundles sorry, put too many uppies and downies in there. These three vector bundles are isomorphic as vector bundles to the Whitney sum. Oh, sorry, not tensor product. Okay. All right, so this is four representations of one thing, okay? The thing which we did spend a little bit of time talking about, which is this one. And so, like I said, it's easy to see that at least as a set, this thing looks like this, okay? Because this thing, by definition of the pullback, consists of points in the fibers of E and F, which lie over the same point, and that's what the direct sum was as well. Okay, so the hard thing here is verifying. So as sets, this and this and this are in bijective correspondence. That's easy. The hard thing is showing that the vector bundle structure that we gave here agrees with the vector bundle structure here and the vector bundle structure here. Okay. So, that's where you have to understand the vector bundle structure of the pullback. Okay, good. So that's these two. Let's look at this one. So again, let's just look at the first part of the diagram, okay? And so the definition of pullback bundle, this, says we take points in M cross E cross F, okay? Whose images under the image of the point in M under this mapping agrees with the projection here. Okay, well, what does this mapping do? Okay, it just takes a point in here and maps it to the product of that point sitting inside M cross M. Okay, so it's X. If I take a point X here, then it's X, X. Okay. And so now, according to the pullback construction, I consider points here which map to points of the form X cross X. Well, again, this is just telling you that I'm going to take points in E cross F which have the same base point, okay? And so again, as sets, it's easy to see that as a set, this thing is in bijective correspondence with this thing. Okay, and then the hard part is verifying that the vector bundle structure that we built for this agrees with the pullback vector bundle structure. Okay, but it does, and I don't wish to trivialize that, but what I hope at least is it gives you some intuition for how pullback bundles work. You have some vector bundle here and you want to basically translate do something with the fibers. Okay. All right, so I think that's a good place to stop for today. I'll close talking about vector bundles tomorrow by doing two things. The first thing I'm going to do is give you some vector bundle constructions So, if you're familiar with geometry a little bit, especially finite dimensional geometry, I'm going to tell you two common constructions from finite dimensional differential geometry that don't work, at least not easily, in infinite dimensional geometry. And then we'll talk about the notion of section. Okay, and after that, we'll talk about what are called affine bundles. And affine bundles, as we'll see, are going to show up when we talk about derivatives of mappings. Okay? All right, so that finishes the lecture, and unless there's questions, I'll sign off.